All right, before I begin on the worksheets, I would like to offer a brief review of Trig, hitting the high points. Remember, on the exam, you're not going to have a calculator. So you're going to be required to know the trig function values of pi over 6, pi over 4, pi over 3, or any multiple of those, and that also includes 0, pi over 2, pi, and 3 pi over 2. Of course, we recognize these as just the corners of the unit circle. So let's go over a way to remember these. Now, the whole point of view when I teach this is to try to get you to be able to be very functional without having to memorize a whole lot. Because in the heat of battle of an exam, it's kind of hard to remember all this stuff. So for pi over 4, I always like to begin with that one. We have a square and draw a diagonal. Now, by the Pythagorean theorem, this is the square root of 2. A square has right angles, 90 degrees, or pi over 2 radians. And this diagonal will bisect those angles. So this becomes pi over 4. So we can see right away that the sine of pi over 4 is going to be the opposite over the hypotenuse. And when you rationalize that, you get square root of 2 over 2. The cosine of pi over 4 is the adjacent over the hypotenuse. So it is also 1 over the square root of 2. Square root of 2 over 2. Now, as we've seen in class, that's all you need to know. The other 4 trig functions are written in terms of sine and cosine. So this is the minimum amount you need to know, right? Now, if you write it like this, this helps a lot, because then if you want the tangent of pi over 4, just put your pencil here. Tangents, by definition, sine over cosine, so it's this over this, or just 1. Cotangent of pi over 4 is going to be the reciprocal of the tangent. Well, that's 1. The reciprocal of 1 is 1. The cosecant of pi over 4 is 1 over the sine of pi over 4. And I like to use this form. If you take the reciprocal of this, you just get square root of 2. Secant of pi over 4 is going to be 1 over the cosine of pi over 4. And that's going to also be the square root of 2. But you know, I don't remember these because I can get them just from this information. So that's got that squared away. Now, what about for pi over 6 and pi over 3? Well, these are what we call cofunctions. I've mentioned this in class. These add up to pi over 2 radians, or 90 degrees. And a really curious thing happens when you have cofunctions. So let's draw an equilateral triangle, all sides equal to 2. That means the angles are all the same, which is 60 degrees, or pi over 3 radians. Now I'm going to drop an altitude here. An altitude is a line from this vertex to the side opposite, forms a right angle. It also cuts it in half. So this is going to be 1. And by the Pythagorean theorem, this is square root of 3. So it's 1, 2, square root of 3. 1, 2, square root of 3. So this has to be pi over 6. It's half of pi over 3. So we can get from this the sine of pi over 6. Here's the angle. It's going to be opposite over hypotenuse, which is 1/2. the cosine of pi over 6 is going to be the adjacent over the hypotenuse. And the cool thing about angles that are cofunctions, that the sine of pi over 6 will be what the cosine of pi over 3 is. The cosine of pi over 6 is what the sine of pi over 3 is. Personally, I remember this. I remember these. And just like from above, up here, if I know the sine and cosine, I can get the other 4 trig functions. Okay, so that's got me squared away on pi over 6, pi over 4, pi over 3, or any multiple of those. Now, draw a unit circle. Unit means the radius is 1. Okay. Now, this is where we began, which is 0. Now, if we go all the way around, that's 2 pi radians. If we go all the way around again, that's 2 pi again, so that's 4 pi. And it keeps going. So the thing to know here is if that coefficient's even, you're right smack here. Now this is pi. If you begin here and go around, this is pi radians. If you start here now and go around, you add 2 pi to that, you get 3 pi. Go around again, you get 5 pi. So over here are the odd multiples of pi. So for example, if someone said, okay, what's 117 pi? What's the sine and cosine of 117 pi? 117 is odd, so you're going to be right here. So the sine is 0, cosine is 1. So let's draw an arbitrary angle here. So this is our angle theta. Now if I draw in a line parallel to the y-axis, that's going to find a right angle there. Now this coordinate is x and y. So here's the x value and here's the y value, and of course the radius is 1. Now the definition of the sine of this angle theta is going to be the side opposite, which is y, over the hypotenuse. So we see that y is just sine theta. So we can rewrite this coordinate as a sine theta there. And the definition of cosine theta is going to be the side adjacent over the hypotenuse. So this is cosine theta. So when you see the cosine function, it's just an x value. You're plotting, you're looking and thinking of just the x values as you walk around this unit circle. The sine is just the y value. Now the tangent of this angle is going to be defined to be the opposite over adjacent. So that means sine theta over cosine theta. The cotangent of theta is defined to be adjacent over opposite. That's going to be cosine theta over sine theta, or 1 over tangent. So if you know sine and cosine, you automatically know the tangent. Just draw a line like this. The cotangents are reciprocal. Now the cosecant of theta is defined to be 1 over y, the hypotenuse over the opposite. So that's 1 over sine theta. So if you know the sine of the angle, you take the reciprocal, you get the cosecant. And finally, the secant of the angle theta is 1 over x. That's 1 over cosine theta. So if I can find the sine and cosine, then the other 4 trig functions will follow directly from that. Okay, now just a little more for our little brief introduction. So, if we take a unit circle, let's try to clear up something that's in the text. It always bothers me a little bit. Your textbook starts by drawing a line like this and saying that this is t equals, say, pi over 4, and they give you this coordinate as the square root of 2 over 2, square root of 2 over 2. Now, how in the world are they getting that? Well, for any circle, the subtended angle, theta, is the same thing as the arc length over the radius. That's true for any circle. In our circle, the radius is 1. So therefore, the subtended angle is the same as the arc length. Now, theta itself is an angle measurement. Positive is this way, counterclockwise. And theta is dimensionless. A radian has no dimensions. It's a pure number. Well, when we say theta is equal to s, remember there's a 1 here. So if this distance is measured in meters, then the radius is measured in meters. But here's the deal. For a unit circle, this distance here is the same as that angle. So if this distance, if you've walked pi over 4, a distance of pi over 4, that means this angle is pi over 4. So see, the circumference of any circle is 2 pi times the radius. Our radius is 1. So 1 trip around is 2 pi radians. It's 2 pi feet. If you want to think of this as feet and the radius is feet, it's 2 pi feet, a little over 6 feet around. Inches, it would be a little over 6 inches. Miles, it would be a little over 6 miles. So look, we've walked a fourth of the way. A fourth of 2 pi is pi over 2. So that angle is pi over 2, and that distance would be pi over 2 yards. About 1.5 yards, 1.57, something like that. Okay, and now I've already showed you how to get this for theta equals pi over 4. So that's how they do that. That's how they introduce this. So now and this is going to be how they get their graphs. Just think of wrapping a lot of cord around here. And what if we could paint this white and this green and this blue and this red? And then think about taking this rope off and laying it like this. So if this was white, you would have the white marker here. I forget what I said this was. Green, maybe. You would have a green at pi over 2, a length of pi over 2 here. We're just unwinding the rope and putting it here. Now, if we go halfway around, there's going to be that color right there. And then 3 pi over 2, this piece of the rope. And then all the way back down then to 2 pi. So for instance, if you're graphing, if you want to graph y equals sine t or y equals sine theta, what you're plotting these y values as you go around. So at 0, I've got a y value of 0. So right here, at pi over 2, the y value is 1. Let's put 1 right there. At pi, the y value is 0. At 3 pi over 2, the y value is minus 1. So say somewhere like that. Try to make it consistent. And back at 2 pi, you're 0. So you get a graph like this. You're just graphing the y values. Why are you just graphing the y values? Because the sign is a y value. Now, if you want to do the same thing, and look at the graph of y equals cosine, it begins at 1. Remember, for a cosine is an x value. So you're beginning here, and you're going to plot the x values as you go around. So it begins at 1. And then at pi over 2, the x value is 0. Right? So it's going to go like this. If we keep going around, at pi radians, the x value is minus 1. So something like this. Okay? At 3 pi over 2, the x value is 0. So this is going to come down here and then start coming back up. And then when we get to 2 pi, the x value is 1 again. So that's what a cosine looks like. Now here's the cool thing. If I take the sine function and shift it to the left by an increment of pi over 2, I get this curve. I get the cosine. Or if I take the cosine and shift it to the right, see, this continues back this way. If I take the cosine curve and shift it to the right. So I can get the cosine curve by taking the sine curve and shifting it to the left, distance of pi over 2. That is really cool. Or I can get, if I begin with the cosine curve, if I shift the cosine curve to the right, the cosine of t minus pi over 2 gives me the sine curve. Okay, one more thing and we'll be finished with our little review. Now this is just the briefest of reviews. And I want to go over this last part. And now this is just for the introduction of the trig stuff. If we have a unit circle, if we have a unit circle, in each quadrant, there is one and only one multiple of pi over 6, pi over 4, pi over 3. And that's true just for these guys. For instance, if you're interested in pi over 12, there are several occurrences of multiples of pi over 12 in each quadrant. But these are the ones you're going to be primarily interested in on an exam. So if someone says, what is the sine of 31 pi over 4? Here's all you do. Take 31 pi over 4. Now I'm going to go one more unit of pi over 4. So that would give me 32 pi over 4. Or I'm going to go one less, which is 30 pi over 4. One of these two, when you reduce it, will be an integer. In this case, it's this one. 32 pi over 4 is 8 pi. 8 pi is right here because 8 is even. So this is 32 pi over 4. This is 1 less, which means 31 pi over 4 is right here. Now what do we know? We know that the x's are positive and the y's are negative. And see, the neat thing about radian measure, if you want to know the reference angle of this angle, if you want to know the reference angle of 31 pi over 4, cover the 31 up. The reference angle is going to be pi over 4. Okay, so I can say then that the sine of 31 pi over 4 is going to be exactly what the sine of pi over 4 is, except plus or minus. I don't know which. I have to figure out where this angle lives. Well, now I know it's down here. And the y values are negative. So that means the sine of 31 pi over 4 is going to be the same as the sine of pi over 4, but negative, because the y values are down here, and the sine function is a y value. So this is going to be a minus square root of 2 over 2. And that is all there is to this mystery of finding the sine or cosine or the tangent or the cotangent or the secant or cosecant of any multiple of these things. It really is the simplest thing in the world once you get it, because you're just going around in circles. Let's do another one. Let's find the tangent of 27 pi over 4. Well, cover the 27 up. This is going to be what the tangent of pi over 4 is, except plus or minus. It's that easy. That's your reference angle. Now, if you're using degrees, this is much harder, I think. So now let's figure out where 27 pi over 4 is. Here's 27 pi over 4. If I go one more pi over 4, that gives me 28 pi over 4. And if I go one less, I get 26 pi over 4. One of these will be an integer. Well, it's this one, isn't it? It's 7 pi. 7 pi is over here. So 7 pi is 28 pi over 4, and we're one less. So it's going to be right here. Well, now, what do we know over here? We know that x's are negative and the y's are positive. But what do we know about the tangent of pi over 4? Remember, for pi over 4, sine and cosine are the same. So the tangent's going to be 1, but these are different signs. When the signs are different, that means the quotient's negative. Finally, one last example. What is, say, the secant of, what are you going to do? Good one? How about, what do you think? What do you think? 58 pi over 6. Holy moly. Well, okay. This is going to be the secant of pi over 6. That's the reference angle, plus or minus. So 58 pi over 6. Now let's see, this is 59 pi over 6, or 57 pi over 6. And we have a problem, don't we? We have a problem. Can you see the problem? Neither one of these are integers. Well, what's going on? Why doesn't this work this time? Did I lie to you up here? 6 doesn't go into 59 evenly. 6 doesn't go into 57 evenly. The problem's back here. See, 58 pi over 6 is really what? We can take a 2 and get a 3. We can take a 2 and get a 29. It's really 29 pi over 3. So let's mark that out. When this isn't reduced, everything crashes. So we're really being asked, what is the secant of 29 pi over 3? And that is in lowest terms. So now, let's make sure we can do this. Go 1 more pi over 3, you get 30. And I'm not even going to check the other one. 30 pi over 3 is 10 pi. So 10 pi is right here. And we are a pi over 3 less. So it's got to be right there. Now again, the x's are positive. And remember, a secant is positive. So now I've got this reduced. My reference angle is going to be the secant of pi over 3. And in quadrant 4, I know it's positive. So this is going to be 1 over the cosine of pi over 3. That's 1 over 1/2, or 2. Okay, let's discuss graphing just very briefly, the general form of a graph. For reference, I'm going to use this. I'm going to hold on to these curves for reference. I know it looks like this. It has a period of 2 pi, and it goes from 1 to -1. So it starts at 0 and does that. I get one complete sine curve. Now I wrote an x, but you could put a t here, or you could put a theta for cosine. Well, see, if you take the cosine curve and shift it pi over 2 units, you get the cosine. If you take the sine curve and shift it pi over 2 units to the left, you get the sine curve. So if you know the sine curve, you can get the cosine curve. It starts like this. Okay, 2 pi, 1 -1. I'm going to keep that as reference. Tangent. It has period pi units. Now remember, tangent sine over cosine, and the cosine is undefined at pi over 2 minus pi over 2, 3 pi over 2. And what you get are infinitely many branches like this. I just remember one of them. That's all. Cotangent. Now the cotangent is, remember, cosine over sine. So it's going to be undefined where the sine is 0. Well, the sine is 0 at x equals 0 or t equals 0. And then the sine is 0 at sine is 0 at 0, and then at pi. So it's going to be periodic, period pi. Pi over 2. And it looks like this. Okay? And you just get infinitely many copies to the left and to the right. Now, y equals cosecant. Let me show you a little trick to remember cosecant. And it just takes a minute. I'm going to draw in the sine curve. Now, the reason you need the sine curve is cosecant's 1 over sine. So where the sine is 0, you have a vertical asymptote. So the sine is 0 at pi, at 0, at 2 pi, minus pi. Now, this is 1. This is a sine curve. This is a sine curve. So I want the reciprocal. Well, the reciprocal of 1 is 1. But now as the sine values get smaller and go to 0, this thing is going to spring up to infinity. But it's asymptotic like this. So I don't remember what the cosecant curve is. I just remember the sine curve. And I'm going to take the reciprocal of it. Let me see if I can find a different marker. So I get the graph of the cosecant function from the sine function. I don't memorize what this does. Every time I've got a question involving cosecant and the graph, I always draw the sine curve. But you see, it's periodic. It's periodic with a period of 2 pi. Over any interval of 2 pi units, I get one complete cosecant curve. See that? Now, again, I'm just drawing reference stuff here. If I want to look at the graph of y equals secant x, well, secant's 1 over cosine, so I'm going to begin by drawing the cosine curve. Or you can draw this as a t, but then this is going to be the t-axis. It doesn't matter. So I'm going to draw the cosine curve here. Okay, now it goes back this way too. So the cosine is 0 at pi over 2, 3 pi over 2, 5 pi over 2, minus pi over 2, minus 3 pi over 2. Those are going to be vertical asymptotes. So you just sketch the cosine, and you're interested in where the cosine is 0. And then now you want to draw the reciprocals. See, I've got the cosine looks like this, so the cosecant will be the reciprocal of that. The cosine looks like this, cosecant's reciprocal. And it's periodic with a period of 2 pi. Over any interval that's 2 pi units, you get one complete cosecant. Okay, there's a half-hour review of trig in just its most elemental form. Now let's look at some worksheets.